I'm Yong Kim from KAIST, and I'm pleased to be here. And first of all, I'd like to thank the organizers for the kind invitation. Today, I'll talk about some recent result on the target search problem. What is the target search problem? This is the Nasdaq index over the last 5 years, and recently we worry about the depression and high spiking interest rate, right? So because of it, it's recently falling. And suppose that you invested a year ago, then you might wonder your stock price will recover the price, right? And in this case, we have animals, and they are wandering around the territory for foraging to find a food or shelter, right? And also we are also in the living in the era of a pandemic. So the simplest model explaining the pandemic is like that. We have the susceptible, and the susceptible encounters the infected with a certain probability and get infected and get, of course, after some time recovered, right? And we have also beautiful microscopic examples such as diffusion control reaction describing bacterial chemotaxis and finding specific DNA sequences by DNA binding proteins such as a promoter, right? Okay, all these problems look very different in different discipline over different length scale, right? But they are in fact interrelated and can be categorized in statistical physics as a target search problem. So this is the definition. We have a searcher performs underlying dynamics to arrive at certain target state, right? Or a certain target position. And as we have seen in the previous slide, this is a universal problem. We experience this kind of problem every day. Then the central question will be, how long does it take for a searcher to encounter a target, which is usually referred to as the mean first pass time. And this is a central quantity in this business, which we want to understand here. Okay, how to formulate the problem? There are many different approaches to tackle this problem, such as linear theory or using the analogy to the electrostatic problem, right? But one of the fundamentals is based on the Fokker-Planck equation. In fact, this first passage problem or target search problem was originally formulated by Kramers and Smolchowski almost 100 years ago to describe chemical reaction. And this is the setting they considered. We have metastable potential, then we have a particle. This particle or reaction coordinate escape from this metastable region to reach here. And here, the potential suddenly change into negative infinite, which means that we have a perfect observing boundary, also location of target here. Then we want to estimate the mean first passage time or mean exit time, the time required to escape from this metastable region. And this can be calculated using Fokker-Planck equation here. For diffusing particle, this transition probability to find a particle at R prime at time t, given initial position R, satisfies this kind of equation, right? Then this is a survival probability that the particle is not observed until time t, which is again given by the positional integral of the transition probability. And this is the first passage probability that the particle absorption or barrier crossing or target finding occurs for the first time at time t. Then you can easily see that the mean first passage time defined previously is given by the average time with the weight of the first passage probability. And then integrating by part using this, then you can show that it is related to the time integral of the survival probability, and further related to the transition probability, right? Okay, then the transition probability itself is expanded using the eigenfunction phi, eigenvalues gamma of the Fokker-Planck operator. Then mean first passage time defined before is expressed in terms of phi and lambda here, and applying the backward Fokker-Planck operator on both sides, then you can derive the backward Fokker-Planck equation for the mean first passage time. So this is the second order differential equation. That means given boundary condition, this quantity can be calculated. As a simple example, suppose that we have a simple one-dimensional diffusion without any external bias, and you put a reflecting boundary here and observing boundary on the other side, then integrating this equation twice with this given boundary condition, then mean first passage time is calculated as a function of initial target position. So in this simple case, everything is just as expected. The mean first passage time is given by the time scale to diffuse over system size with diffusion constant d, right? Okay, this is a picture of a load in our campus in KAIST, and some students call it endless load. Why? It is a pathway to a nearby marketplace with many puffs and bars. So after drinking at night, you have to take this load to get back to your dormitory. But with too much of a C2H5OH, sometimes you become like this, and you feel that the road is winding and you make a completely random step, right? But next morning, you don't remember anything. Still, interestingly, you find yourself in your room, right? How is that possible? You can prove it actually. So the starting point is the renewal equation. Okay, this is the occupation probability, the previous occupation probability, but in discretized time step, right? So probability to arrive site X after n time step or after n random walk. And this F is the first passage probability to arrive at the site X for the first time in J step. And it's decomposed like this, which means that we arrive at the site X for the first time in the previous J step, and for the remaining n minus J step, I don't know here what happens, but there should be some equations here, but sorry, that's my fault actually. Okay, but I'm trying to give some explanation just using a word. So anyway, the physics is simple. Then we arrive at this target site in the previous J step, and for the remaining step, we make a simple returning loop, right? And this equation expresses that. So in that sense, this occupation probability is expressed in the convoluted summation, right? So we have a convoluted summation, therefore it is natural or useful to generate a Laplace transform, discrete Laplace transform or generating function, right? So here is should be a definition of a generating function. So we have a pxz instead of a time step bar x0, right? Then it is given by the summation of original p with e to the minus st, right? And then long time behavior of this function can be studied by this generating function, where the discrete summation is replaced with the continuum integral, right? And then in the continuum integral, we also apply the sharp cutoff approximation. That means we have this Laplace transform factor, e to the minus st, right? And s gives the inverse of time scale. So that means if you neglect some this integral upper bound of a time scale, which should be given by the in that case, in the Laplace notation, 1 over log 1 over z, right? So this is the of time scale. So that means long time behavior, where time goes to the infinity, can be studied by considering the limit where z approaches 1, right, in the Laplace transform. Okay, then if you suppose long time behavior, if you focus on the long time behavior, then the of a simple diffusion, then the probability distribution of a simple diffusion is still given by the Gaussian distribution. And then you put definition of Gaussian distribution in this Laplace or generating function definition, right? And you put you let z approach 1, right? In that way, you can study the long time behavior of occupation probability using generating function, right? And then also you see that thanks to this linear equation, the generating function of f is related to the generating function of p, right? Which also define the survival probability itself, right? So in this way, following this scheme, you can calculate or estimate the long time behavior of survival probability. Probability, the particle is not observed until time t. And you can, from this asymptotic behavior, you can see that this survival probability has interesting dependence on the dimensionality, which is unknown here in this slide. But I hope some other formulas are still there. Okay, only in the introduction slide. Okay, anyway, there is a final expression for the survival probability, and the answer is that in the low dimensional system, survival probability becomes always 0, while in high dimensional system, the survival probability becomes finite, right? And this asymptotic behavior, long-time behavior, depends only on the spatial dimensionality, and details of random walk doesn't matter, right? As a result, to find a home or a target with a random step of a drunken people, drunkard, is always 1 if you are moving in 2 dimensions. But so even if you are completely drunken, then you don't have to worry. You will always find your place, your way back to home. This is for sure. But this is not the case if you are moving in 3-dimensional space. So drunk bird cannot find home, right? Anyway, and this dimensionality dependence can be understood by a simple scaling argument. And suppose that we have a d-dimensional random walk, then the radius of explored by the random walk is given by the walk dimension. So this radius is proportional to the time with the power of 1 over walk dimension. And this walk dimension is usually 2 for simple Brownian motion. And also the number of sites visited by a random walker will be proportional to the time, and the total number of sites within the volume explored by the random walker is proportional to the t with the power of a fractal dimension, right? So in order to get some sense, you have to compare the walk dimension and the fractal dimension. And then the fraction of visited site is given by the total number of sites within the volume divided by total number of visited site by random walker. Then if you put some expression obtained here in this expression, then you see that the fraction of visited site is given by the t to 1 over d over 2. Here d is a dimensionality. So that means in dimensions larger than 2, this fraction of visited site becomes vanishingly small. So which means that you almost never visit any site, right? So in that sense, the random walk is also called transparent. Sorry for that. Anyways, I should have checked that before. Anyway, okay, this classical subject of target search problem has regained a growing interest recently and has been extended in various directions to consider different situations. For example, you can think of target search in complex environment, such as scale invariant network or crowded intracellular medium. Also, you can think of some different dynamics other than simple diffusion, Brownian motion, such as Levy flight or fractional Brownian motion. Also, you may bring up with another idea, such as the motility of searcher or target. So in this way, there are many literally abundant literature devoted to this problem. And this simple classical subject provides a fundamental understanding in many interesting phenomena. Okay. However, most of the previous study considered a single searcher. Then it is natural to try to extend the consideration to incorporate the presence of multiple searchers competing for the same target, right? So suppose that we have n particle or n searchers instead of one. Then what will be the answer? One important question is like that your searching time is still given in this way. I mean, in terms of a single particle searching time renormalized by the number of searcher. If so, what will be the exponent alpha? Is it 1 or any other value? Not easy to answer. So suppose that we have searchers more than 1. Then the problem is already complicated, even in the case of non-interacting particles. Why? We have an non-interacting particle with given initial position like this in domain, and they will record first passage times respectively, right? So we have a n first passage time, but from the point of view of the first passage dynamics, only minimum value is meaningful, which means that the order statistics is necessary, right? And this can be, of course, can be obtained by full first passage time distribution, right? So this is the problem we consider here. We have n non-interacting particle in a finite domain of volume V in dimension D. And we have a target in the center. So I'm going to skip the detail, rather focus on more recent result. But anyway, you can solve this problem analytically. Because for non-interacting systems, trajectories of particles are independent of each other. So the full n particle distribution function is decomposed into product of a single particle distribution. So after some mathematical manipulation, you can find the analytic answer. And after assuming a uniform initial distribution, then you can show that the mean first passage time exhibits a universal behavior like this. When the number of searcher is small, then the gain in searching time is proportional to the number of a searcher. So it is given by 1 over n. While when you have large number of searchers, the gain is more enhanced. It is given by 1 over n squared. And using numerical simulations, we confirm our theoretical prediction. So these symbol, the simulation result performed for different system. I mean, the different system for different size, different number of particle, even in different dimensionality, right? So as you can see here, all the numerical data or symbols are overlapped with each other, right? So confirming our analytic theory. So we have a universal behavior here. Okay, let's move on. In the previous example, we considered a uniformly distributed particle initially, right? But this is only one possibility, right? You can think of different strategies employing different initial distribution. And in first passage problem, one of the key questions is to optimize the system parameter to reduce the mean first passage time. In that sense, important question will be what is the optimal initial distribution of particle to minimize the searching time. Okay, this is a problem we want to consider here. Now, target position is given by a probability distribution function. What does it mean? So target position cannot be fixed, right? If target position can be fixed, then you just put every resource to the target position. This is not target search problem, right? Suppose that instead we have a missing child who was seen an hour ago lastly over there, so at some point. Then you may guess the current position of this child as Gaussian distribution, right? And you have 100 policemen, right? Then how should we deploy this searching skirt? You can think of a broader distribution or narrow distribution or the same as the target distribution. What will be the best, right? This is my question. Then formulation basically remains the same, except that the target position is now given by the probability distribution function, and then you want to minimize this mean first passage time as varying the probability distribution of target PS here. And let me give you some example, simple case example to get an idea. We have a Gaussian target distribution in a finite domain, and the target is most probable at the center. And you have a single searcher, then what will be your choice of a starting position? Natural choice will be the center, right? Where the target is most probable. And this is actually calculated mean first passage time as a function of the target position. And clearly, as expected, it is minimized when you start your search at the center. Quite obvious, right? But what to expect if you have searchers more than one, like a 2 or 3? You think that, is it still most efficient to put 2 searchers, for example, at the center where the target is most probable or not? The answer is no. So the efficient way is to put 2 searchers separated from each other with a certain distance. As you can see here, this is the searching efficiency as a function of first searcher and second searcher's position. And this kind of behavior can be understood by collective searching efficiency. When initial positions of searchers are identical or too close, then searching domain tend to be mostly overlapped, which lowers the searching efficiency, right? So in this way, you can increase the number of searchers to get the exact answer of optimal distribution. But this is a highly correlated problem. So exact answer of optimal distribution for arbitrary n particle is very difficult to understand. In that sense, we propose an alternative approach. In fact, it is not possible to deploy every one of particles precisely in a highly correlated manner, even if we know the exact answer of optimal distribution when you have Avogadro number of particles, right? Instead, we propose an independent deployment scheme, placing particles according to a simple prescribed identical distribution, given like U. 5 minutes? Okay. Then we want to minimize this, we want to find the minimum distribution U to minimize the mean first passage time. Then it's equivalent to taking the functional derivative with respect to U, and then you can find that this optimal distribution is given by the 1/3 of the original target distribution. This is the exact answer, and using the numerical simulation, we confirm our analytical prediction. So here, for example, using Langevin dynamics, we generate the target position as a Gaussian distribution, and also we generate the initial position of searcher according to this arbitrary distribution with different value of gamma, right? And this is the inverse of searching time as a function of gamma. Then clearly you see that the searching time is minimized here. This is the inverse searching time, minimized here when gamma is equal to 3, right? As consistent with our theoretical prediction. So best way is put your searchers a little bit broader than the target distribution. Okay, so we have been considered first passage dynamics by many searchers, but they are still non-interacting. Then important question again will be the effect of interaction. In fact, in most cases, there are some form of interaction between searchers, between particles, right? For example, predators such as whales and wolves communicate with each other to locate or hunt the prey. And more importantly, the first passage dynamics itself was proposed originally to describe the chemical reaction of molecules. And molecules experience various kinds of potential, such as DLV potential, Lennard's potential, right? Then what is the effect of potential on the searching time? This is a question we would like to answer finally. And of course, we know that in many body systems, rigorous consideration of interaction is always non-trivial and one of the fundamental challenges in theoretical physics, right? As an example, let me remind you of how we understand the effect of interaction on the equilibrium pressure for real gas, non-ideal gas. We know that the pressure is given by the virial expansion in this way, but in order to derive this, we have to take a little bit complicated procedure, right? So we consider at first canonical partition function with the Hamiltonian given like this. P is momentum, U is the interaction energy. Then configurational integral is again expressed in terms of moment expansion. Here 0 indicates the average with respect to non-interacting system. Then to calculate the thermodynamic potential, log of partition function should be considered and expressed in terms of cumulant expansion. But still, it is important to remember that this cumulant expansion or moment expansion is perturbative approach, valid only for weakly interacting system. So problematic for strongly interacting system, such as particles with hardcore potential. So in order to consider the general form of interaction, you have to do partial resummation, like a resummation of all 2 point clusters in low density system even. And then you can see that all reducible clusters subtracted out in the variance and all irreducible clusters appear in the final expression in the power of density, right? And then usually it is convenient to treat this cluster expansion in the grand canonical ensemble. Then you obtain the final expression for the pressure given in the form of virial expansion, right? So this is the equilibrium situation and well known for statistical mechanics class. Now let's get back to our original problem. Wow. I'm not sure what's the problem with this PDF file. Anyway, okay, try to use your mind to imagine what will be there. So our problem originally, dynamical problem, we have n interacting particle searching for a single target in a finite domain, right? Then it's a dynamical problem and we want to calculate what is the mean first passage time. So that means in order to get an answer, you have to solve the Fokker-Planck equation for n interacting particle system, which is obviously non-trivial task. You have to, for example, generalize the previous approach of equilibrium, which is already complicated, to the dynamical system with the time domain, right? And of course, I cannot show the detail, and I will skip the detail, but we have tackled this problem and found that kind of a sort of a partial resummation is also possible for the solution of a Fokker-Planck equation. And this is the final answer. The result should be here. And the mean first passage time is given in the form of a virial expansion. You can show that. Actually, we have shown that result. And so this is a correction of mean first passage time to the compared to the non-interacting system. And it is given by the proportional to the virial coefficient times density, right? And the advantage of this expression is that result is now written in terms of virial coefficient V2 here. So this is a universal result, right? So valid for any kind of a potential. So we have demonstrated this universality performing Langevin dynamic simulations considering different kind of potential. So we have checked with exponential potential, Lagrange potential, Sutherland potential, hardcore potential even, with different number of number of particle, system size, different dimensionality, right? So these all different symbols actually indicates the numerical result from different systems with different potential, and they are nicely collapsed on a single straight line as predicted by our theory. As our theory gives you the mean first passage time is proportional to the mean first passage time non-interacting system multiplied by 1 minus 4/3 virial coefficient and density. Okay, okay, the final summary slide is okay. And let me summarize. We have considered the target search problem by multiple searchers when they are non-interacting and initially uniformly distributed. Then we have a universal scaling behavior with respect to number of searchers. And when they can be arbitrarily adjusted for the initial distribution, then the optimal distribution is proportional to 1/3 of the target distribution. And finally, when they are interacting, this dynamical problem can be tackled. It will be complicated, but can be solved, giving the final answer in the virial form. And most important part, this work was done by my former PhD students, Dr. Seung-Han Roh, currently at MIT as a postdoc, in collaboration with Professor Ju-Yeon Lee in Busan National University. So I'd like to especially thank these collaborators, and I'd like to thank you all for listening, and sorry for the mess up in the slide.
Thank you for the very interesting talk. I think we may have time for one quick question. Yes.
Thank you for the great talk. I didn't catch what the coefficient B means. So if you want to increase the search efficiency, do you want attractive force or repulsive force between the searchers?
Repulsive force. That's
repulsive force.
This is the usual second virial coefficient that you can find in the textbook, and so it is given by the Mayer function, right? So if we have repulsive force, then usually it gives you some small value here, for example, then it is a positive. And when you have a positive contribution, the final answer, it is given by the 1 minus virial coefficient. So searching time is reduced. So that makes sense, actually. Why? If you have a repulsion, then the particle try to keep a certain distance among them, right? So it will increase the searching efficiency because the searching domain can be compartmentalized or separated.
Yeah,
If you have a strong attraction, then the particle will form a strongly aggregated cluster, so they are not very widely moving, so searching efficiency is very small.
So maybe if the repulsive force is too large, maybe the searching,
Yes, of course,
but this scheme might fail.
In that case,
large.
This is a visual density expansion case, so valid only for the low density system. But if you have a very large density of strong repulsion, then they will make a kind of a Wegener crystal, right?
Oh.
So if you have a Wegener crystallization, mobility drops to zero, then searching does not happen.
Okay. Oh, thank you very much.
So I think we should continue because we're already fairly advanced in time. So let's thank the speaker again. Thank you very much.
Thank you.